Hey there, astronomy students. It's Miss Ruark. We're in Chapter 5. We're starting off Chapter 5 by talking about Newton, Einstein, and gravity and all the work that they did with gravity. So let's jump in. All right, Newton and Einstein, they brought about a new era of science, and they did all of their work. I was getting to that, but they used math because they were both physicists. So they came along and put math in astronomy. It's great. I know you guys love it. So Newton is who we're going to talk about first in this one. Newton was around from 1643 to 1727. He did all of his work based on the results of Galileo and Kepler. And he is known for adding physics interpretations to all of the astronomy that we know now based on Copernicus, Galileo, and Kepler. So, you want to thank somebody for all the math that we're getting ready to do, you just thank this guy right here. All right, major achievements. He did three major things. He invented calculus, so you can go thank him for your lovely calculus test. He discovered the three laws of motion, and he discovered the universal law of mutual gravitation, which we're going to cover those just a second. All right, velocity and acceleration. When we're talking about motion, we need to talk about velocity and acceleration. So acceleration is the change in motion. Okay, and velocity is the rate at which that change in motion happens. So acceleration is the change of a body's velocity with time. So the formula we would have for that would be A is equal to delta V over delta T. This right here is the capital is lambda, and we call it delta. It's the Greek letter lambda. It stands for delta. Am I saying that right? I think so. Anyways, it's delta stands for change. So this is the change in velocity over the change in time. So if we were standing at the top of this tower here and we decided to drop that red ball off of, the balcony there, we drop the red ball off, the acceleration of the object will be going down. Okay, and just because the acceleration of the object is accelerating down doesn't mean that it's a negative acceleration. It's changing its velocity, it's changing its motion as it moves. So the acceleration is measured going down. The velocity is also going to be measured going down. And to find the change in those, we would take the final velocity minus the initial velocity and this final time minus the initial time and divide those to get the acceleration. All right, well, if we did that, we'd find that the acceleration of this object would be 9.8 meters per second. That number is very important. Why? Because that's the pull of gravity. We love that number. All right, so velocity and acceleration are directed quantities, which means they are vectors, and that means that you have to have a direction with them at all times. So velocity is the rate of speed. It's speed with direction, okay? And acceleration is the change in motion with direction. All right. Different cases or different ways to look at acceleration. You can accelerate in the conventional sense where you increase your speed. You can decelerate or decrease your speed. That would be a negative acceleration. And you can change the direction of your motion. So you can go around in circles. And all three of these cases would be considered acceleration. All right, acceleration of gravity. Galileo decided he wanted to figure out if two things dropped from the same spot that had different mass would hit the ground at the same time. So he took an iron ball and a wood ball, and he decided to drop them from the top of the Leaning Tower of Pisa. And the iron ball, of course, had more mass, and the wood ball had less, and he dropped them, and he found out that they both hit the ground at the same time. So acceleration of gravity does not depend on the mass of the falling object. It just depends on gravity. All right, well, this is difficult to prove on Earth because there's an atmosphere and we have air and it gets in the way and it causes air resistance. So guess what happened? I don't remember when, but there was a lunar mission where they actually took a hammer. You can tell there's the hammer and a feather, which is in here somewhere, and they dropped them on the face of the Earth. And because the Earth does not have an atmosphere, there's no air resistance, and they both fell at the same time, and they both hit the ground at the same time. So this proves that the acceleration of gravity is independent of mass. All right, Newton's laws of motion. We'll go through these pretty quick because you've already seen them. So the first law is the law of inertia, which means a body at rest stays at rest, or a body in motion stays in motion in a straight line at constant velocity unless acted upon by an outside force. So this astronaut here is going to float off into space if he gets knocked off the space station, and he's going to continue to float forever and ever and ever unless he gets hit by an asteroid. Sorry, it was gross. But, you know, that would be the outside force acting on him, right? Otherwise, he's going to keep going, same rate, same direction, everything. Nothing will change unless a force acts upon him. All right, second law tells us that force, mass, and acceleration are all related. So it gives us this nice equation here, F is equal to m times a. And it says, hey, guess what? If I put a force on this mass right here, it will accelerate. Whew, that's some deep stuff. All right, so there's a couple ways you can look at it. You can say that, hey, the mass of this object and how fast I want to move it will tell me how much force I need to put on it, and that would be F is equal to ma. Or, how far will it accelerate? Well, if I push on it this much and it has this mass, it'll go this fast. Okay, so a force on a mass will accelerate. All right. The third law of motion deals with action and reaction forces. So every action has an equal and opposite reaction force. All right, so how does that work? Well, think about pushing on a wall. If you push on a wall, that's the action force, but guess what? The wall is pushing on you at the same time. That's the reaction force. Okay, that would be a balance force because neither of you is going anywhere. Well, here, there's a skateboarder, and he's pushing against the ground, and that would be the action force. But then the reaction force is when the ground pushes against the wheels of the skateboard, and he goes back or goes forward. So, all right. Universal law of gravity. Okay, we've covered Newton's laws of motion. Now we're in his law of gravity. So, any two bodies are attracting each other through gravitation. Everything has a pull of gravity, no matter how big or small it is. It just, if you have a lot more mass, you have more gravity. If you have less mass, you have less gravity. Okay, well, guess what? We're going to have to do equations. Yay, more math. So here's your lovely equation. You've got F is equal to a negative G times mm over r squared. Make sure it's a big M and a little m. All right, so all of these letters mean something. Well, F stands for force. G stands for the universal constant of gravity. Since it's constant, it's going to be the same thing every time, which means you're going to be getting it on a reference sheet. The M and the M stand for the mass of the two objects, and then the R stands for the distance between those two objects, or the distance between the masses. We'll do some calculations with this in class. All right, orbital motion. So the universal law of gravity helps us to understand how planets and moons orbit around each other and how they orbit around the sun. So an example of this is the Earth and the moon attract each other through gravitation. So the Earth is here, the moon is there, and then the moon is attracted to the Earth and the Earth is attracted to the moon by that force of gravity, and it goes around the Earth. All right, since the Earth is much more massive than the moon's effect on the Earth is very small. Okay, and that's why the moon goes around the Earth and the Earth doesn't go around the moon. All right, now what's to say if the force of gravity wasn't there and the velocity of this moon was going around, it wouldn't keep going around in a circle. It would actually just kind of, you know, with inertia, it would just keep going straight, right? All right, so Earth's gravitational force constantly accelerates the moon towards the Earth. Okay, so it's pulling it, it's pulling it, it's pulling it. Okay, and here you would be able to see the difference in the velocities. Okay, and this acceleration is constantly changing the moon's direction of motion, so it's constantly accelerating, holding on to its almost circular orbit. All right, well, in order for an object, a closed orbit, an object has to be within a certain range of velocities. So what does that mean? Well, let's say we're on top of this mountain here and we want to shoot this cannon off, and the ball inside of here, we want it to go all the way around this path and back and hit it here and just keep orbiting. All right, well, in order for that to happen, we have to get the velocity, that force that we're kicking that off with, to get the velocity, we have to get that right. So what happens if we are too slow in our velocity? Well, if we're too slow in the velocity, we don't put enough force behind it to get the velocity where it needs to be, it's going to fall into the ocean right here. It's just going to land. It's done. All right, that's not good. We want it to go around and around and around. So we have to hit it with some more. Well, let's put some more power behind that thing and fire it off again. And this time, guess what? We're too fast. What happens? Well, now it's going to escape the Earth's gravitational pull and it's out in outer space. No good. So it has to be just right. All right, Kepler's third law explained by Newton. So Newton came along and did some more work with Kepler's stuff. Kepler's law was pretty crazy looking, but guess what? We can actually use Kepler's law and make it pretty easy. Okay, so balancing this force, this centripetal force necessary to keep the object in circular motion with gravitational force, we can use Kepler's third law, which is P squared is equal to A squared, A cubed, excuse me. All right, so, go back. The P stands for the time a planet takes to travel around the sun one time. So we call that its orbital period. And the A stands for the average distance from the sun to the planet, and that would be measured in astronomical units. And when you come to class, we're going to use this to calculate. Yay, more calculations. All right, the moon. We said that the moon has gravitational pull. It's smaller than the Earth's, and that's why we don't feel it that much. But think about things that are smaller. Would those things that are smaller be able to feel it? Well, think about the water in the oceans. That water in the oceans does feel the pull of the gravity. Okay, so the tides that happen are caused by a difference of the moon's gravitational attraction to the water on Earth. And the forces are balanced towards the center of the Earth here. However, if the moon is on this side, it's going to be closer to the water on the moon side than it would on the other side, and so it's going to pull all the water towards it, which causes these bulges. Okay, these bulges is where that excess gravity pulls together, and it's going to end up creating these tides. And don't worry about those two things. Well, this right here just tells you have two tidal maximums, and this is a 12-hour cycle, so you'll end up every 12 hours you'll hit that same one again. All right, so you can have two different types of tides. We can have a spring tide and we can have a neap tide. All right, the sun can help create these. So if the sun and the moon can get together, they can have a pretty crazy force here, because the sun produces a tidal effect that's about half as strong as the moon's. It's bigger than the moon, but it's further away, so we don't feel it as much. All right, so near full moon and new moon, the sun and the moon will actually line up together, and their forces will actually go, they'll add together, and it causes this extreme tide to come in, and they're a lot bigger. Well, near the first and the third quarter, you end up having them working against each other, because the sun's pulling here and the moon is pulling here or here. They kind of cancel each other out, and it makes a really small tide, which we call neap tides. All right, acceleration of the moon's orbital motion. So this right here, what this is telling us is, okay, so the Earth or the moon pulls on the water and causes the tides, but the Earth can exert tidal forces on the moon as well, and the rock on the face of the Earth can be shown to kind of flex, and these tidal forces can affect the orbital motion, or the way that it goes around, the way that the moon moves around the Earth. And it shows that the moon's orbit as it goes around is actually growing a little bit larger. It's growing by about 4 centimeters per year, so it gets a little bit further out just because of these moon flexes. Okay, so the Earth's tidal bulges are slightly tilted, and they're slightly tilted in the direction of the Earth's rotation, and then those gravitational forces will pull the moon slightly forward along its path, along its orbit. Okay, so it pulls it slightly forward to it, but it's actually going to end up, I don't know why that's there. I don't know why that's there either. All right, we're not getting to that yet either. All right, so it's actually going to end up making the moon's orbit grow just a little bit more because of the elliptical motion of it. So, yeah. All right, so that sums it up. That's all we need for this first one. When you guys get into your second podcast for this unit, or for this chapter, we'll get into Einstein and his theory of relativity. And I'll see you in class.